Hello everyone, today I'll be presenting our work on iterative and/or graphs for task and motion planning. Task and motion planning is referred as combining high-level decision making, which is represented in discrete space, with low-level motion planning, which is represented in continuous space. The mapping between task planning and motion planning is the interaction of these planners. Many task planners have been developed from which PDDL-based planners are the center of attention. Various motion planners, either deterministic or stochastic, such as RRT and PRM, are used commonly. Many methods have been proposed to be used as task and motion interactions. Semantic attachments have gained many interest among researchers. Planner-independent interface layer and abstraction and refinement methods have also shown to be effective. Recent works investigated streams method as an interaction between task and motion planning layers. However, to use these methods, one needs additional expertise and full knowledge of PDDL-based planners to set them to comply with state space search of the planner. In our approach, we encode task-level abstractions efficiently within an and/or graph. This graph can grow to a point that the goal state is reached. We propose a task and motion planning interface for interaction between and/or graph and motion planner, which requires no additional expertise. Our approach allows fast planning compared to traditional task planners. The computational complexity of our approach has shown to be quasi-linear, while traditional planners have exponential behavior with respect to the complexities. In traditional planners, the number of tasks should be known in advance, while the task representation of our approach allows us to set the task space to be unknown in depth. To evaluate our approach, we perform some sort of experiments. In this experiment, robot is supposed to retrieve the target object, the cylinder with red tape, from a cluttered table. To do this, traversing an and/or graph, robot has to pick and place objects to the storage to make the target object reachable. In this scenario, we restrict robot to do side graspings. Ungraspable objects, like the bugs in this video, are removed by pushing them. The process continues until the target object is picked. In the representation layer, one graph is added to the main graph for every object rearrangement. As you can see in the video, if the object is not graspable, so like the box, robot has to push the object, and if the target object, as soon as the target object becomes reachable, robot tries to pick it. In this figure, an instance of growing graph that we use in this experiment is shown. Every graph corresponds to one object rearrangement, and graph grows to the point we reach to the goal. As you can see in the graph, there are various parallel hyperarcs to reach the goal. For instance, if robot is not able to pick target at first attempt, then box needs to be pushed. And if this is not possible as well, then closest object to target or closest objects to the end effectors need to be removed. We perform many experiments to evaluate the computational complexity of our approach. The quantitative results are listed in this table. Representation layer of our approach that embeds and/or graph and tree search as the solver are very fast and are less than 1% of overall time. Motion planning and execution time form the major portion time of our scenario. It's not noteworthy that we have different depths of graphs for the same number of objects, and we relate this fact to the stochastic nature of the motion planners. In this work, we introduce an efficient framework to target task and motion planning problems. We adopted and/or graphs to model high-level task planning instead of the traditional task planners, and finally we describe an instance of task and motion planning scenario and evaluated it in the robotic scenario. Thanks for watching.